Alright, just a little bit of notes for today. So we're going to review Newton's second law, and we're going to use Newton's second law to solve for problems. Remember, our objective for this entire unit is to be able to calculate acceleration, knowing the net force that's acting on a mass. So remember, F net stands for net force. Sometimes people get confused with F sub n, but F sub n just means normal force, and we're going to talk about that in a little bit. But F net means net force, and that's simply the sum of all the forces acting on an object. And we're going to use newtons, or just capital N, when we measure force, any force including the net force. Okay. Remember, M is going to stand for mass, and that's just the amount of matter, and that doesn't change regardless of where you are in the universe. And we are going to always use kilograms to measure mass. We could write this out if we wanted to, just so you remember what it is. Okay, kilograms. And remember, A stands for acceleration, and our units for acceleration are simply meters per second squared. That's just the amount of speed that an object gains per unit of time. So it's the rate of change of speed. Okay. For weight versus mass, remember we looked at that, and that wasn't 05, it was actually 08. Okay, so hopefully you did that lab. But we know that weight is the force of gravity on an object. Sorry about my handwriting today, it's not very good. And we're going to use newtons to measure weight. And mass is simply the amount of matter, right? So we're going to use, like I said above, kilograms for that. And we should know now that we can calculate weight based on an object's mass, because weight, and I don't really like to use that W, I usually use force due to gravity, is the same as weight, is equal to m times g, right? Where m is the mass and g is 9.8 meters per second squared as long as we're on Earth. And for the most part, that's where we're going to be. So force of gravity, Fg, is just equal to mg, and it's the same as weight. Okay. Let's see, normal force, we haven't talked a lot about normal force, but normal force is the force, usually force acting against gravity. From a surface. So for instance, if your iPad right now is sitting on a table, the table is exerting a normal force on the iPad so that the iPad does not fall. Okay. So the normal force is usually equal to the force of gravity, just in the opposite direction. That's what that negative sign means there. And of course, its units are still going to be newtons. Okay. Some reminders for a free body diagram. Remember, we're going to use a dot for the object. Right, we don't actually have to draw a box or a table or a chair, whatever we're doing the free body diagram for. Remember, the back of the arrow always starts on the dot. And remember that the length of the arrow, I don't know how to spell arrow apparently, length of the arrow represents the magnitude of the force. And magnitude is just a fancy word for size. Okay? So all pretty straightforward. So let's go ahead and do a sample problem. All right, here is our sample problem. We have a tug-of-war challenge. One team consists of 12 boys with a combined mass of 960 kilograms. The other is 15 girls with a combined mass of 1,000 kilograms. We want to know what is the weight of the participants. So all together, their mass is 1,960 kilograms. That's a lot of people. Okay, so if we want to calculate weight, which is just the force due to gravity, we have to equal that's mass times g. So that's 1,960 kilograms times 9.8 meters per second squared. And when you do that math, you should come up with 19,208 newtons. Check that in your calculator right now. Pause the video, check that, and see if that's what you got. Okay. Part B is asking if the girls pull with 460 newtons of force and the boys pull with 400 newtons of force, what's the acceleration of the system? All right, so let's go ahead and draw a free body diagram. And this is basically of our system. So it's the boys, the girls, the ropes all together. Let's say that the girls are pulling to the right with 460 newtons, and the boys are pulling to the left with 400 newtons. So notice how that left arrow should be a little bit smaller than the right arrow. Okay. So we can figure out the net force from that, from our diagram, because our net force has to be 460 minus 400, so it has to be 60 newtons. The net force also has to be equal to the mass times the acceleration. So that 60 newtons has to equal the mass, which we know is 1,960 kilograms, times the acceleration. So go ahead and plug that into your calculator, see what you get for your acceleration, and then come back to the video. All right, you should have gotten that your acceleration is 0.03 meters per second squared. Now, what if you drew this differently? What if instead of drawing a free body diagram the way I did, what if you said, oh, well, the boys are pulling to the right with 400 newtons, and the girls are pulling to the left with 460 newtons? What would you have gotten then? Well, then your net force would actually be negative 60 newtons because we have more force to the left, which we have chosen as our negative direction. So that negative 60 newtons would have equaled the 1,960 kilograms times the acceleration, and our acceleration would be negative 0.03 meters per second squared, which is fine. That just means that we're accelerating to the left. So it doesn't really matter which direction you go. You just have to remember your signs. Okay? All right, that's it for today. Have a great day. Thanks. Bye-bye.